All right, everybody, we're just getting back in. Okay. All right, the attendance is slowly building up. Let me just see if I can get myself connected here. This is where we were at. All right, let's see if I can just open another lecture. This will be lecture number 10. Okay. All right, let me just, I guess we're still having some students taking their time to come in. There are about 11 students now. But we are being recorded. Excuse me. And let me just send a quick message. Okay. All right, so we're about 20 now, some 5 strong. It's about half the class. And I always insist that students participate in these lectures. It will be helpful to them. And I certainly understand because of the circumstances we all live in. It takes a little bit of energy to actually be able to get on these Zoom lectures. But, look at the other side of it. I mean, if we were to do this on campus, you would have to drive to campus and then actually go to the classroom physically. So right now you may be in the comfort of your own house or wherever you live and just, just get on that computer and you're right face to face with your professor and also classmates. That's what makes this maybe not too bad an alternative. In fact, my thought is that this may become a way of teaching in for many years to come in the end, with all the congestion that we experience, in our routes here, locally speaking. So let's get back to class. And so we're going to, try to finish things up today. I'm a little bit sort of like phased today because we just lost our dog. And, but I will try to keep it, on the subject. So what we did last time, we looked at these 2 instructions, right? So our goal is to now make use of these instructions in order to be able, thank you, Ekta, thanks. We'll take a look at these 2 instructions and see how we can use them to simplify things and avoid self-modifying code. Okay, so last class, we covered.
Professor, you're not sharing your screen.
Oh, I'm not sharing my screen. You're right. Let me just go back for a minute to the other part of the screen here. Okay. All right. MXF and MXT instructions. Okay, so we did those last time. And what we're going to do, we're going to use them today to simplify VESP programming, let's say. So we have gone from, VESP 1.0 to VESP 2.0. Let me just also mention that, we just basically transitioned from VESP 1.0, and we, did that last time, to VESP 2.0. So the key difference was that this was 8 instructions, machine with 8 instructions. This is 16 instructions. Okay. And the other point that I made was, VESP 2.0 was backward compatible. Whatever code we wrote for VESP 1.0 will also work for VESP 2.0. Okay, now let's take a look at that example we did in class, like with self-modifying code, and see what kind of simplification we can expect from this new machine and its 16 instructions. So now let's see. Let's go back to that example. Let us go back to the program, the example we did before. We worked with self-modifying code. So it was like this, right? Everybody remembers that? Okay, so example revisited. And it's this example. We said, let's just say we clear something called sum. And we said, we had an array which we initialize. An array to some n elements. Our n was equal to 10. Okay, I'm not going to write that in C or anything. It's just basically some n, 10 element. You can say a bracket, n. You can define n to be 10, whatever you like. But those are the things that we had to do. And then we had this loop for I from 1 I less than or equal to n I plus plus, and then we said sum is equal to sum plus, this array maybe a I. Okay, that was our loop. And then we did the self-modifying code. So what we're going to do, we're now going to write the same program in the assembly level without using self-modifying code. And you can see that if you just look at the memory structure, let's actually map it out here. In the earlier edition, we these are always reserved locations, 0 and 1. This is like our A, this is our B. And then we had set this up as our IX. That's location 2, sorry. we set this up as IX, okay, you know, virtual maybe like we created it ourselves. And then we put the sum over here, okay. And then starting at location A, hexadecimal, these are all hexadecimal numbers. We then put in all the way to location 13. These are, again, you know, like I just have to maybe write this. These are all hexadecimal numbers. I'll just say, you know, I'll write it and then, okay, hexadecimal, you can say 0x and that, but hex. So this is where the array was. And down here, let me just make this a little longer. Down here, we had the program begin, location 20. So not much will change in terms of the layout of the problem because we now have a proper physical IX, okay? So virtual in 1.0, physical in 2.0. Okay, so I can maybe write some little more than what I've just been able to put in there. This location 2 is virtually serving as an IX in VESP 1.0, like VESP 1.0. And in VESP 2.0, it actually serves as a physical IX. We actually have this register physically inserted into the machine's architecture. It's now there. We didn't have this capability in the earlier edition, and neither did we have the so-called MXF and MXT instructions. What MXF instruction does, as I explained to you last time, it actually provides an accessing or an indexing mechanism where you go grab a bunch of numbers from the memory one at a time and then put them into a target, like a mux I said. So in other words, in this instruction, which we call MXF, we have this capability. You know, it begins with an E, that's the hexadecimal code, and then we write some number, for example, 003. That means move whatever IX points to, move that operand in memory into a location that happens to be 3 in this case. And if you notice, that's our sum location. But we may just want to move it maybe not to the sum as much, but we may want to move that maybe to like maybe the B register. Okay. Move an operand from the location that is pointed by IX into B. B meaning like, you know, register B basically, right? That's register B, co-accumulator.
Professor,
Yes, sir.
what is the difference between like physical and virtual IX? Like, how are they different?
Let's say that you are, you know, can you put yourself on the screen?
You mean like share my
Okay,
video?
now you are, I'm looking at a virtual copy of you. That's
Okay.
not physical. On my screen, you're virtual. Wherever you are, you're physical.
Okay.
Right? I can't touch you. If I just reach into my computer screen, I won't be able to touch you. So to me, you're a virtual image. You're just a bunch of pixels that I'm able to see.
Right.
You're not real.
Oh, okay. I think I kind of get it. Like there's like a physical component that is different.
You're physical. If you just, pinch yourself here, like you're going to hurt. You're going to feel the pain. I can't pinch you to make you feel pain.
But when you declare a virtual IX register, right, you're just reserving a specific register as saying like, this is going to be the IX register. And
So
I'm
the
going
physical means that I actually put it into my machine physically.
Okay.
Whereas I could have declared location 25 or maybe 126 as a virtual IX.
I see. Okay. I see. Thank you.
Okay. And try to pinch yourself and, get that physical feeling. Okay. You can turn off your screen if you want, but that's what I meant. Physical versus virtual. Something really there, something only virtually there. All right, now we explained that, hopefully. Let's get back to the thing. So just try to pay attention to this E001 business, right? So what that means is that now we have some location, which is really pointed to by this address that sits in the IX, which is now physical. That's part of our architecture. And we don't have to specify it. If you think about the move instruction, it always had two components. The first 16 bits and then the second 16 bits. In this instruction, there's no such 16 bits. The second one disappeared because we now have a special purpose register, which we call IX, that actually tells us where the operand will come from. That is what this instruction does. And the other thing it does, it actually increments the IX by 1 once we use this instruction. That means it automatically takes us to the next location. So this is like scanning through a bunch of locations in memory and then grabbing them one at a time and putting them into a particular location where we can do some more processing with it. That's what we're doing here. Right, so that's what we're going to use. We're going to use this E instruction without having to have a second 16-bit put inside underneath it. And that simplifies, first of all, it makes our program more compact. We can just do away with those next 16 bits. And the other part of it is we don't really have to use what's called this self-modifying code idea by having two move instructions back to back. And those instructions would have taken 4 places because each of them would use two 16-bit memory locations. Now, all of that can be replaced by this. And on top of it, we don't really have to increment the so-called this virtual register IX by 1 every time we go through this loop. And so now we save a step in that regard as well, because the IX gets incremented. So many advantages here are all, built into this 16 instruction architecture. So let's now, this being a critical instruction, okay, so we will basically the pair of move instructions. I can't get these, fit in the right way. Fortunately, I have that eraser. By MXF. Okay. Also the IX, also the physical IX is incremented by VESP itself. Okay. We don't have to worry about incrementing, that virtual IX because we had to sort of like go through the locations in memory. All right. So now let's go and maybe organize our assembly code. Okay. We don't have to worry about, I guess we still have to do something about the IX. Let's make sure that we can actually initialize this. So now let's just, write this. Okay. So we're going to go ahead and do this. Okay. Where's the program? All right, I'm just going to go to the next page. All right, so we assume that our array is located in location A, so we're going to have to initialize ix, which is actually still a location which we can initialize. So we're going to load into it a value, which is going to be, I'm going to write it actually underneath here, and we want to put 0, 0A. Okay, and then we want to clear the sum. Okay, clear the sum. Okay, now we have to load our numbers. Okay, let's go ahead and do that also. So we will have the complete program written. So I guess we will just, let's say that this is location 20 hexadecimal, 21, 22, 23. Now we're writing into 24. These are all hexadecimal locations. And now we want to put the numbers in. And as we did before, I'm going to put into location A, number 1, into location B, number 2, into location C, number 3, it's not here, into location 2A, number location D, number 4, into location E, number 5, into location F, number 6.
Professor, are you writing anything?
Say it again.
Are you writing anything?
You're not seeing it?
Yeah, I don't see it either.
The last thing we see is 2A. The
Oh, you don't see my screen anymore?
The last thing we see is the location. Okay, now it's coming.
Is it coming? It must have frozen for some reason. Okay. So like 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 9, A, B, C, D, E, F. We still have to write some more numbers. Okay, let me just actually fill up this space so that I can, when I go to the next place, I will be using only the loop part. So I'm going to write basically, we were at 2F, so we're going to go to 3, 0, 3, 1. Let me just write some numbers here. 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. Let's see what else I have to write. So I am at 3, 0, and I'm going to put into location 2, 0, 1, 0, number 7. Into location 2, 0, 1, 1, number 8. Into location 2, 0, 1, 2, number 9. And into location 2, 0, 1, 3, number 10. Okay, so this completes copying or initializing our array. All of these steps right there, all of these together initialize A. Okay. So now we've done all this stuff. We just have to go into the loop. So let's go take a look at the loop. All there is left to do is the loop. We initialize everything that we wanted to initialize. Now we want to go ahead and basically take care of the loop business. Okay, so now so now we're going to go ahead and do the loop. All right, so remember now, the way we did the loop was to check to see if we're actually at the end of the loop or not. In other words, we reached a point where our so-called the index position happens to be equal to 14. If that's the case, we will just exit out of there, okay? So, and we did that by simply putting a 14 into, I guess, register B or register A, and putting the IX into the other register, and then performing a subtraction, and then going from there on, okay? So I don't know exactly which way I wrote it, but it doesn't matter which way we subtract. So I can put, for example, I can move, okay, so this is the loop area. 14 into the accumulator, okay? So we put the 14 into the accumulator, and this is, by the way, location number 38. This is 39. Okay, and then we put the index register into B.
Professor, by putting 14, we are checking if we have reached the end of the loop.
Yeah, because 13 is the last place that we put something in if you just look at it here. 13 has a valid value, 14 doesn't. So I'm going to check to see if we reached that point. Okay, so I'm going to put into B the other number, okay, which will be actually coming from our IX as before. So basically load 14 into A, the accumulator, copy IX into co-accumulator. One is copy, one is load, as you can see. I'm using 3 for copying, 2 for loading. Okay. And then now that I've done that, I want to complement what is in actually A. I cannot complement B, so I'm going to have to just, do a complement. So that's 3C, and complement was this opcode. It hasn't changed. Okay. And then I simply add now at this point in time, the two of them together. Okay. So we get a sum. And I can now destroy the B register because I have the sum of the two numbers, the complemented 14 and the so-called index value that happens to be in 1. So now I load into the next step would be to put a, actually, let me just do this. I think now we can simplify things here also. I just remembered. So at this location, one of our instructions, if you remember, let's just go back here. Instead of like putting 1 into B and then adding it to A, if you remember, now you may not because we didn't spend much time on this, except I just listed them. Let's go back to the table. There's a nice instruction in there. You notice that, right? Everybody? Do you see that instruction there? What instruction is that?
Increment.
So it's going to increment A. Instead of like putting a 1 into B and then adding it to A, we just use this instruction. Okay, that will save us an extra step because we have to load a number and then an add. So let's go ahead and use that, which, by the way, you see that that's actually 8 opcode wise. So we're going to go ahead and put that in. Okay. So here we have, like, so this 0, 0 just completes the addition, right? So basically, by the time we do this, which will be 8, 0, 0, 0, by the time we get here, we computed basically minus 14 plus ix. Okay. And if ix has become 14, this difference will be 0.
Is that an 8?
Yes, 8. Like opcode 8. Like add is 0, increment, complement is 1, etc. And this is increment. But why do we do this incrementation? Because we're doing 2's complement subtraction. That's how you do subtraction in 2's complement. You take one of the 2 operands, complement it, depending upon what you're subtracting, but we don't really care in this case because we're looking to get a 0. Okay. So this will basically, okay, so we have this. Now we want to check if this is equal to 0. Okay. So how do we do that check? That's the same instruction that we used before. 3F. That was 5. And then we have some address which we have to determine, like X, X, X. So we don't know where to go yet.
Professor,
Yep.
I think your iPad started lagging again.
Like, is it back? It
No, we can't. Unless you just wrote 5xx, right?
Yeah. You see it?
Yeah, no, we can't see that.
You cannot see it.
No.
No, you cannot see it. Yeah. Okay. So that means, and I don't know what, what Zoom is doing now, something that used to work beautifully all of a sudden started to work. I stopped to work. I'm sorry. Started to act up on us. What do I do? Let's see. I think I can try this. Let's see. I have some power on my computer. I'll drop that pen again. If I could get this ever. Okay. All right. So let's see if I could do this. And maybe, I'm not sure if this is going to kick anything into gear. Okay. So if I do that, what happens?
Yes, it shows now.
It shows now?
Yeah.
All right. I will just keep iPad charging here. Maybe that will just work it out. I don't know. Hopefully it will. So that will just be some XXX locations that we have to go to. Now, if I don't go there, this is where I have to do my work. So now if you remember, this is, by the way, by this time we're at location 40. Correct, yep. So now we have to do the following. We got to put the sum, we cleared to 0, which we have to now bring into A, and then use that MXF instruction as opposed to using those 2 move instructions that we used to have. And then simply add the 2 together and then store the sum back, and don't worry about incrementing the IX because it's always going to be incremented by itself. So here we do this. So we want to bring the sum into A, and we know that the sum is in location 3. Okay, so now that brings the sum. Accumulator is equal to sum. And now we want to do this move by way of this IX register, right? So that is our so-called MXF instruction. And all we have to do is say E001, which is the one I showed you up here, if you remember. That instruction right there. With that particular 00, it doesn't have to be 001. It could be any address. But now we want to bring it to B. It's not like that's cast in iron. You can never make it anything else. You can always put anything that you want into these 3 places. This is like our register B. That's why I'm using it. Any address is a fair game there. Okay, so that means, IX, not IX, sorry. B is equal to co-accumulator is equal to MEM IX. As soon as you execute that instruction, you get this done but also you have ix equals ix plus 1. So now you copied the running sum into A, and the other part of this summation that you have to conduct now comes from location that is pointed by the ix. And now the only thing that you have to do is, there's left to do is basically add the 2. And then don't leave it there, because if you leave it there, it's going to be destroyed. So you cannot afford to leave it there. Save it back to where it came from. So in location 14, you go take it back to the location 3, and that completes our basically summation process. But we have only done it one iteration. We want to do this 10 times. Don't worry about ix. Ix gets incremented by 1. We used to increment ix because it's virtual, not real. Now ix is physically incremented by itself. VESP does it on our behalf. So the only thing that's left to do is to go back to the beginning. And we have to do a forced jump. So where's our loop? Our loop is basically here, right? We go back to this location 38. So we can check to see if, in fact, the thing in ix has become 14. This increment will not make it. Initially, it was set to, I guess, location. What is it? We put it in location, I guess, A, right? Now it's going to go up to location B. Just take a look at these numbers here, right? Location A, location B, location C. So by the time we completed this iteration one time, it becomes B. The next time it becomes C. It becomes D. Sorry. You're able to see these things that I'm doing? Right, everybody?
Yeah.
So all the way up to location 13. That is still okay, but it must end when we get to 14. So the location we go back is 4038. Now we know where we should actually exit. That's location 47. And that XXXX becomes 047. Okay. And that is a halt instruction down here. I think if you compare this to the other code, I think we used to go to 53. Now we're at 47. So we saved ourselves quite a few steps, quite a few memory locations, right? 53 minus 47. These are hexadecimal numbers. So you have, what is it? 19 minus 7, which is equal to 12. And then you have a carry of 1. So I think it's, it's more than 12 locations that you saved. Okay. Now we can execute this, and then, we can, let me just, maybe we got some time. I'll do another, couple of other programs, and then maybe we can just run them, towards the end of the. Another thing you can do, for example, all assembly language level, you can do lots of other things. For example, you can search for an entry, right? Another example. I'm going to assign a homework problem by this weekend, and that will be about programming VESP. And so I think, I want to do a couple of examples today. So, and then if time permits, we can run these programs. Otherwise, you just have to copy these. In fact, here's what I'd like to do. Now, some of you may have extra time, or not extra time, but time to actually maybe like listen to me at the same time, type this stuff into your VESP simulator. Not everybody, but someone can actually go ahead and put all the stuff that we did. And we have some 36 students in class. Maybe one person can just enter all these things. I don't know. I mean, I cannot say you do it because, I'm going to tell you some things here that, you may not be able to pay attention. So I cannot force anybody to actually putting this code into VESP and trying it, because it's a very laborious process. And of course, if you do it, you want to do this on not VESP 1.0, but VESP 2.0, because VESP 1.0 is not going to recognize MXF. So let's say that we want to search, for example, in that same array, we can make it somewhat more random than the way that we filled it out. And let's say we want to look for an element. It's simple search. Like let's say that we do just linear search, not a binary search or anything. In other words, our list is not sorted. We just have a bunch of numbers, and then we want to find out, if an element that we are looking for happens to be in that particular array, right? So if it is in there, and what we want to do is maybe just copy the key that is the index position where that element is found and save it into maybe some place, right? So search an array of elements. For an element, okay? And sometimes they call this a key, and store its index in a reserved location in MEM, the memory. Okay, so this, you could also write it as a simple loop. For example, you can say for I1, I less than or equal to maybe some number n, I plus plus, and say, like if MEM of I is equal to some key that you have, then maybe some location A is equal to I, okay? And then just simply do this, all right? Basically, this is like your for loop. I don't have to put braces here, but okay. So, like I goes in there, otherwise you don't change A. So you can clear A, you can initialize A to some negative number, whatever you want to do. And then, if I shows up, then that key is actually in that position. And this will find the first location where that key is. And if you have multiple copies of this, it'll only find the first one. Because if you use quantum search, like Grover search, you can actually finish the search in square root of n time, as opposed to like n time in the worst case. And in the average also, if you just add those numbers from 1 up to n, and then divide it by the number of elements in the list, so you would still get something like n over 2 is the average number of iterations that this sort of a loop will go through to find that element. But you can always search this if you actually had a quantum architecture, quantum computer, in square root of n time. That is a known fact. But now we're not doing quantum computing in this class, so we're not going to see how that gets done using Grover search. Okay, but if you're interested, there's always ample material in that whole World Wide Web, as they call it. Okay, where you can find a lot of information as to how this gets done. It's basically a filtering process, but a very clever one at that, and requires some quantum states for it to work. All right, so we're going to do this now in assembly. I mean, in machine code, that is, not assembly. And so we have to create, again, as some kind of a data structure for this, albeit very elementary. So let's say that we, still have only 10 elements as we had before. Now, we're not going to sum something this time. We're going to be searching something. So we can actually replace that sum location by this thing called A, where we will actually dump that I into that location. So let's see, so you can see what I'm doing here. Maybe you can, you don't have to do it this way, but this is a good, safe way. First, you understand how you do it in a high level language, like here, sort of like pseudo program. And then you begin to sort of like see, okay, what are my key variables here? A is a key variable, I is a key variable, and there is actually something that I am searching, which is what I call key. So a key is a critical variable. And then of course the array itself, okay? So you got to get these things, all created in the assembly layer. That's what, by the way, compilers do. They actually create the machine layer in this case. They create a machine language, ultimately version of that same thing. So now let's go ahead and do this. So here's our memory map. You're able to see what I'm writing? I think it was an issue of power here. I don't know why that happened. I do have power on both machines, so we should be okay. So here's how it should look. Again, A and B are off limits. We cannot put anything in those places, but now IX is also off limits. Okay, so A, B, and IX. These are basically already physical registers, okay? Physical registers. All right, now we can just create this thing called key, okay? And we can initialize a number in there. So let's just actually put that key in there as our next location. Okay, and that's what we're searching for. The item being searched. And then finally, we want to basically get the index. This is, I think, I. Index of the item. If found. Okay, so that's how you search. So this is location 0, location 1, location 2, location 3, and location 4. So this time we have
Professor?
4. Yeah.
So is I, in this case, A from the pseudocode?
Yeah. That's right. Actually, this is, you can call it basically location A. I think, thanks.
Okay,
Dave.
great.
Yeah.
Thanks.
Yeah, sure. Let's just call it A. Holds, let's just change it like this. Holds the index, okay? Holds the index. That's where we're going to dump the index. It's not the location itself, but the index will go into that place called A. Okay, so now that's like, that's what we have. And then of course, again, as before, we've got our array begins, at this place, like A. It runs up to 13. This is all hexadecimal. And then down here, we have the code. Okay, so if I can stretch this. Okay. Maybe down here, we have our code starting at location 20. Our code. That's our array. So this is critical. I think you want to draw this sort of a diagram before you jump to coding, because you know exactly where things will be. This way you create a map. And in other words, this is really called memory mapping, and it's automated in real machines. Okay. Compilers generate these variables, they assign them to virtual locations, which are then translated into physical locations by the time that this thing gets loaded into an actual computer's memory and waiting to be run. So this is it. This is basically the structure. Now let's go ahead and put everything to motion, right? So we have to basically initialize IX to A as before, because that's where our first element is. And we now have to initialize key to something that we want to search. which could be a number that we choose, and a number would be fine. And then we can also initialize A to maybe some negative number, like maybe, you know, -1 or -2, whatever. Or we can just maybe, you know, clear it to 0. And therefore, you know, we could say that it will not be a proper value because our array begins at A and it ends up at 13. So, you know, the number that we're expecting to get there will be some number between those two. And if it's 0, obviously we know that it's not there. We could also generate other things like, you know, we can sort of like maybe have another variable like B, where we put a particular value in there, you know, maybe like a 1 saying that found, and a 0 meaning that we didn't find it. There are lots of things you can do to this, but, you know, I'll just give you the backbone of the code now. So it's the same idea. And how much time I have here, I want to make sure that maybe I punch one of these, but let's see. Let's just, you know, go to work. I will skip some steps. I won't write everything, you know, like from one beginning to end. Not the critical steps, but only the like memory. I'm not going to type everything down. We'll try to figure out exactly where we should be. Okay. So that now the code, here's the code. All right. So the first thing that we want to do is initialize the IX. Okay. Let's go ahead and do that. So I'm going to put into location 2 the starting address of my array. Okay. And, you know, I would then go and take a look at what I have to do is just maybe initialize key, and whatever I'm searching for, I have to put it in there somewhere. And let's say that, you know, because we said it's going to be in location 3. So I'm going to put in some number in there, right? So 003, this is where our sum used to go to. I'll put a number. Let's say they were looking for example, 5. There's 5 there, okay? So I'm going to put 5 in there. Key is 5. By the way, let's just write this 20, 21, 22, 23, okay? And then the next location is A, and that's not something that we're going to, you know, like maybe we can initialize it. Let's just put a 0 in there, clear it, okay? So that whatever number we come up with, if it's not equal to 0, then we know that we found something in there, okay? Because we changed it. So I'm just going to say, let's put into location 4, 0. Okay. So initially, basically, you know, we haven't found the number. It just represents the fact that we haven't found it yet, or we will never find it. We didn't find it in the end. The number, the key is not in the array. In the array. Okay, so now basically we've done all this stuff. What else do we have to do? Let's go down. Okay, so we now have to go to work, right? We basically initialize everything we wanted to initialize and set up a loop and check to see if we're at the end of our loop, much the same way we did before. But we could actually, before we do that, we have to put the numbers in. So let me just go ahead and do that, 26. This is where I'm going to put the first number, right? So I'm going to go in twos, basically. Let me just do the first one. 200A. Now put the number. You know, we can put any numbers in here. I'm just doing this because we've been doing this like this all this time. You can write some arbitrary numbers in there. I mean, this is after all an array that's given to you to see if something is in there. You know, it doesn't have to be 1 up to 10. We're just doing an example here. Okay, so that's 27. And I need to put 9 more of these, right? So 9 more numbers will give me 18 locations. And this is hexadecimal. If I add 18 to 27, what is 18 in hexadecimal? It's 10, correct? So it's going to give me 37. I assume that we're gonna end, yeah, so basically I added, like 10. And yeah, I assume that it'll be like, can somebody do the algebra for me? Because I'm just gonna write this. By the time you get there. Yeah, do the algebra for me and tell me if this is actually correct. Okay,
It is 39, I think.
say it again.
I think it is 39.
Oh, did I just not do the addition right?
So 39 would be
Oh, I have
like
to add, I have
39.
I have to add 12. Yeah, I'm sorry. I just added 16, right? Did you see that I added 16?
Yep.
Yeah, that's why I didn't come out the right way. Okay, so that ends at 39, correct?
Mm-hmm.
Yeah, thank you. Instead of writing this, I just want to save some time. Okay, so this will be like 2013, and then we'll be like 000A. Okay, so the code that I have to write will come after this. Okay, hoping that that's right. I just did the hexadecimal addition. Okay, so now, the array is there, and we initialize what we had to initialize. We put the key in there. We're looking for this number 5. That's what we wanted to see in this case. In this example, you can change it to anything you want. Okay. In our next language, you'll see that we can actually change this rather easily. But here you're just putting into the code itself. And that's why there's always a need for an assembler or an assembly process where you can actually vary that thing and enter it from outside. Whereas here you kind of burn it or bury it right into the code itself. As a result, you get to have basically some fixed code, which you have to ultimately change every time your key changes, which is not a good idea. You will see there are ways to get around this when in fact you're compiling a code and assembling it and then finally translating into a machine code. Okay, in code appeal we're going to see all these steps. It's a very naive technology, this one is, but it is very useful for us to be somewhat connected with the physical sort of side of things. When we go up to code appeal or some such simulator, you're going to end up basically removing yourself from the reality a little bit more. It's going to be more like executing or running things in almost C or Java or something. Not that high, but you will get that feeling that you're removed from reality. Okay, so now in location 3A, we're going to have to start what we have to do. So we're looking for something. And this amounts to basically, a comparison. And comparison is, again, a subtraction operation. But before we get to that, we want to check to see if we're outside of our, array. So what did we do for that? We put in into register A, number 014, that is. Okay. And then we brought the index register into B. It is still in that location. Then we complemented A, which will be 1 0 0 0. And then we added A and B together. And then we incremented what is in A. And now we want to jump, which was 5, and then X, 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 we don't know where. Okay. Now we didn't jump. That means we are ready to make a comparison. And we have a key, which is sitting in location, which we call key, which is location 3. You see that how similar this code turned out to be to the earlier one? Almost identical, right? You notice that our key is actually our sum? Almost. Instead of adding things, we're going to now do another subtraction to see if key is actually what is in the so-called memory location that we're not currently looking at. So that one addition is now going to be replaced by subtraction. Same step, but slightly different operation. Okay, so now, maybe I could write these things. This was basically our array. Okay, all of this is initialize the array. Okay. I don't say A because there's a lot of places in a lot of places. I don't want you to get confused. So now this is basically check to see if we reached the end of our search. Okay. If it's 0, then we get out of there. Okay, so if we don't get out of there, we have to do some work. And what we want to do is to copy, let's say, what is in the array into one place and the key into the other and perform a subtraction. Okay, so let's put maybe the one that we're looking for, the key into A. So that means copy the so-called key, which happens to be sitting in location 3 into A. Okay, copy key into A into the accumulator, and then copy B, copy, not B, but copy the array into B. You see how useful that instruction is? Okay, we copied it into B. And now we want to perform a subtraction as before. So that means we need to complement Isai, baby, I can talk right now. I'm in class, okay? Not right now, though. I'm in class, right in the middle of class. Thank you. Bye. All right. So we just copy this into AC. I mean, we copy that in there. Copy the key. Copy, and then bring this stuff into the memory. Yeah, my daughter's just looking for a vaccine spot for me. That's why she called. But you heard me talk. Okay, let's go back to this. Let's get back to this. I'm sorry. We copy things in the right places. Okay. Now we want to perform a subtraction. That means we have to complement the key, maybe, like we do 1, 0, 0, 0. And now we want to add the two together. Okay. And then we want to do 47 increment, which is actually 8, 0, 0, 0, 0. So what does this do? Well, it simply compares what we just brought into register B with what we have in key. If they are the same, we should get a 0. Okay, so these steps right there. Okay, basically copy MEMIX into B. Okay, that one right there. Actually, this is just a little too far. And these compares basically, key to MEMIX. And then if it's equal to 0, we know that we found it. We simply get out of there. So again, it's going to be 5y, y, y. If not, we force ourselves back into the beginning of the loop. Okay? This is like a premature termination of the loop because we found what we're looking for. Okay. So that will take us back, this 49. We have to make a forced jump, go back to the very beginning, which is location 3A, okay? Right there, we go back here. Okay, so we go location 3A. Okay. Now we used to go to 39 because we had one less step prior. Now we have this thing called location, I guess. Actually, we didn't do anything with that location. I don't know how we got here, but you know, we can check later. Okay, I don't think we made a mistake up until now. Okay, so if we didn't go back to do the loop, you know, we have two places to take care of, right? Either we bail out of you know, that location 41, or we bail out here. In both cases, we actually bail out. Now, if we exited from 41, that would mean that we actually didn't find what we're looking for. If we exited from 48, that means we found what we're looking for. Okay. But in both cases, you know, we have to do something. So let's just go put this, you know, 40, maybe Y business to here. Okay. So let's make it 4A and replace this by 0, 4A. Okay. And what we want to do is now move into, I guess, that place which we call A, the value of I. Now you see that we have to think about this step. When we did use this so-called move instruction, move MXF, what would have happened to IX?
It increments by 1.
Yeah, so that means if in fact we found this index, that's going to be one more than what we found. So we have to decrement that location and then save that into what we call A. So how do we decrement? Just like we have an instruction to increment, we also have an instruction to decrement, but we have to decrement IX. That means we have to copy it into A and then decrement it and then save it, okay? So here's what I'm gonna do. So as you can see what I'm doing, what I just told you, I will do what I just told you. So here's what I do. Copy into A what is in IX, and then decrement it, which is I think 9000. Decrement it. And then save this into location, which we called the location A, which would be 3004. And we want to save what is in the accumulator. So basically, decrement IX and save it into A. A is like that location which we would put the key. And of course, once we do this, we go to halt, basically. 4D is going to be, not 4D, but actually all these numbers are wrong, as you notice, right? We have to get them right. 4B, 4C, 4D, 4E. Now we are in 4F, and that's going to be 7000. Now, where should we jump then from here?
To where you check if you have reached the end of the array.
Well, this is no. We actually don't do that. But here we determine that it's equal to 0, the difference. So we go to halt, basically. Does that make sense, Yekta? You follow that? Right, that's where we basically do the subtraction and found the difference to be 0. This is for the index checking. If it's 0, that means we're done. So that means we come down to the same place. which is this location 4F.
Wouldn't the result of this program give us the memory address of the value we're looking for and not the index?
No, the index of the index of the index where we found the thing, not the value. No. Is that what you were asking?
No, doesn't this give like the memory address of where the value is, not the index of where the value is?
Yeah, I'm just losing. Yeah, let me just see. So this is the A is the location where we want to store something, correct?
Yeah.
Okay. So what are we storing in that location? Just by the program,
We're storing IX.
which has the index value where we found the element.
Yeah,
Okay. Isn't that what we want to do?
I guess. I think I'm just a little confused.
So what should we do instead? What do you think we wanted to do?
I just got to read it over again.
Okay. So we're basically trying to find out at what location is our number.
Yeah.
We want to store that into A, and that's what we're doing here.
I think the confusion might be we're talking about the actual location in memory and not like the variable I from the value of 1 to 10. We're talking about an actual location in memory.
Okay, if that's the question, yeah, we don't want to do that algebra. We just want to know where in the memory this thing is.
Yeah,
Yeah.
Ethan, I don't know if that's what you were going for, but if that
Yeah,
is,
that's what I thought we were going to do.
Oh, okay. So basically, wait a minute. I think so. What we're doing is we're just simply storing it. We're not. Yeah. So here's the question. Okay, I got this now. If you want to explain that, yeah. Okay. Sorry about being a little slow today. So what I think the question is this. I get it. So in other words, our array is not that one. Sorry. Where's the array? Right there. Our array is stored in locations basically A through 13, whereas this index that we're referring to here is like between 1 and n. So I guess the question is saying, are we going to store a number like between 1 and n, or are we going to store some number that where we found this thing, which is a number between A and 13? I think the answer is we're actually, as we do it here, we're not storing the value of I, but we're storing the value of the location where the found element is found, actual physical location. Does that answer your question? Who asked the question, by the way?
Ethan.
Ethan, yeah. Does that answer your question?
Yeah, it does.
Thank you. Thank you. And thanks for asking that question. I think it'll probably, also help other students understand why that may be important. Okay. So let me just, and save it into it. So let me just say that. By the way, I just want to finish this here. This will be that same place that we just ended the program, and that's 4F. So this will be replaced by 0, 4F, because we're going to terminate the code at that point. Let me just, put a little bit of an explanation here. Okay. Here we are saving the physical location of the key in MEM, wherever we found it, okay? And that's more or less what the program is. Now I'm looking at my time, it's 1:42. I wanted to run one of these, but let me also tell you, one other quick example. Maybe I'll do this on Tuesday, maybe, we will move on, but because we got about 3 minutes, I can't run these programs, but, I urge everybody to run these programs and then maybe, report to Xiaomin, or, like just basically share your information. I'll ask questions like this in the actual homework assignment. But another thing you can do, for example, like in the sorting could be another problem you can work on, right? Sorting. So when you sort, there are many sorting algorithms, would be another example. I don't have much time to explain, but maybe I'll do some more of this. But in case of sorting, we need maybe, like if I do maybe, insertion or selection sort or something, then I would have two index variables like I and J, right? You can write something like, for I maybe, like 1 to n, and then you can put a 4 maybe like, J from I to n, and then, you know, compare and then swap. Okay, if need be. Something like this, right? This will be, I guess it'll be selection sort maybe, depending upon how you do it. Something like this can easily be implemented because again, we have just I and J, right? You can just set up, one of them could be your IX. We don't have two IXs. We only have one physical IX. That means you can only deal with, you know, like I or J, and that means you still have to have a virtual index register, and you can just maybe create one right after, you know, the real physical. You can call I, for example, the real IX, and then the next location could be your virtual, you know, IX, and now you have to operate both these variables at the same time so that you can do this nested loop. So you can do lots of things, even on a machine like VESP, so easily. Okay. Now, once we get to finish these things, which will be hopefully next Tuesday, I would then move on to, you know, a lot more powerful assembly level programming tool, as I told you already. And we will see that all these things can be done almost at the high level language. We can write these things just like what you see there. Like, you know, simple loops can be constructed with the stroke of a pen, I guess, as they say, and you'll be done. You don't have to go through this, but we have to understand this because our job in this class, our work in this class is about understanding things, right? The material that we're supposed to understand is what I'm saying. Once you get past these, you know, you become, you know, once you put this in your, you know, in your store, you got this knowledge, you know, you're capable, you don't have to worry about these things, but this is the material we're learning here. This is not like we're going to do things like this in life. That's not what it is. We're learning how things work. So don't try to interpolate from this, okay, I will use something like this in real life. You know, that's not a good direction to go. We're trying to explain things here. All right. I think I'm done for the day. Just can't continue a little, you know, much too longer. Whatever. I'm losing my words. Okay, everybody, take it easy. I'll see you guys on Tuesday next week. We just completed another week. You know, we are on schedule. We are on, you know, we're on target, and we'll just continue to learn more stuff. Okay.
Is the homework going to get released?
By this weekend, Gabe.
All
Ethan,
right.
what?
No, it's Shane.
Oh, somebody else?
And did you schedule the exam yet?
I think, you know, the way it's going now, it's going to be after the spring break.
All right.
When is the spring break, by the way?
I think 14th it starts, 21st, something like that.
Yeah, it'll be right after
to
that.
the 21st.
I think I'll probably give you a week to come back and then, you know, get ready for the exam. Yeah, and then we're going to be looking, I mean, it's just semester is just flying just so fast. All right, everybody. See ya.
All
So
right.
homework 2 is going to come your way this weekend, and then, you know, get it back. Smell like a similar deadline, 2 weeks.
Professor, can I ask a quick question?
Yeah.
Can you go up a little? You know how on location 4A to 4E you said save it into A? Is that the register A?
No, this is like lowercase a, which I think we created to be location 4. Was it 4 or 5? One of these. 5. Why is it 5? Hold on. No, the 5 is something else. Let me just look back here. So A is actually location 4, right? That's 0, 1, 2, 3, 4.
Okay, thank you.
You're welcome.
Have a good day, Professor. I'll see you next time.
Yeah, likewise. Thank you. Have a good day too. All right, everybody. Maria, you have a question?
I do. So the only time we use decimal in the VESP code would be when we're initializing A. because we loaded values 10, 11, 12, and 13.
Just, make it specific. So what would you're talking about this one here? When you say 10, 11, 13 business, like these, like 200A is like 1 or 2 or 3 and so on.
So before, I guess it could be here too. But this was where I'm looking at my notes is right after you wrote here is the VESP 2.2 program, so it's up a bit.
Okay, here's the code.
I think it's
Earlier example maybe.
Yeah. Okay. So yeah, and right here.
Yep. What's the question?
So you're loading.
Wait a minute, let me just. That's 1 there.
Like at 30, you're loading 10. You're not loading A. Is that because that's a?
What I'm loading here. Can you tell me what line is it? Like, you can read the numbers 24, 25. Which location are you referring to?
A. Or
Like
location
2A?
37.
Location which? 37? Yeah, that's number 10.
Right. And then so location
And then before that is
36
number 9, number 8, number 7.
Right. So we're loading, those are decimal, right?
No, A is a hexadecimal number.
No, but 13, like for 36.
13 is actually a hexadecimal number. 19, location 19. I start at location 10. I go to 11, 12, 13, 14, 15, 16, 17, 19, 18, 19. So there are 10 numbers. Between location 10 and 19, Maria, there are some 10 locations.
Okay.
So 13 is a hexadecimal number.
Okay. All right. I got confused.
Yeah, all of those numbers that you see are actually hexadecimal numbers. All these four-digit numbers are hexadecimal numbers.
Okay.
Yeah, I mean, 7 is a decimal number, like also hexadecimal number. They, like hexadecimal 7 is the same as decimal 7.
Right. Okay. Yeah, I missed some letters somewhere.
Okay. Are you comfortable now with it?
Yep. Thank you.
You're welcome. I'll see you on Tuesday. Okay.
Have a good weekend.
You too. Bye-bye. Okay. Let's see. Stop share.